So here, I know we're used to in rate law expressions using those superscripts as reaction orders, but now it's different, guys. But it still is an exponent. You raise it to that power. These are called equilibrium constant expressions. So thus the equilibrium arrow going back and forth. All right, so now we need to switch gears. Notice the little subscript C, and it's kind of like Matthew said, these K's have different subscripts. This one's for molar concentration. We need to switch gears and now talk about a KP. And it's going to be like deja vu, which is good. It's going to be very familiar to you compared to the equilibrium constant expressions that you just did. But KP has not the molar concentrations, but the partial pressures of the reactants and the products. Okay, so I'll show you what it looks like. Does this not look similar? But instead of brackets showing you molar concentrations, it's the partial pressures of the products. It's always the products in the top, right? These are the products. Okay, so the partial pressure of C, okay, raised to its stoichiometric coefficient times the partial pressure of D raised to its coefficient. And then we have reactants down here. Partial pressure of A raised to its stoichiometric coefficient, partial pressure of B raised to its stoichiometric coefficient. Okay. Now granted, these all have to be in the gas phase, but that's quite possible. And I'm going to actually here build up to, if you have a chemical reaction that all the reactants and all the products are gases, you can go ahead and come up with the KP expression, just like that. And actually there is a link between KP and KC for the same equilibrium. Okay. So I'm going to give you a proof. I'm going to kind of prove you through that, but you don't have to be able to do the proof yourself. So let's consider two reactants, A and B, in equilibrium with two products, C and D, and they're all gases. But let's just for kicks go with the equilibrium constant expression in terms of molarities. Okay? Now, they're all in gas phases. So that's the ideal gas law equation. I'm going to rearrange that. PV is equal to nRT. I'm going to rearrange it for N over V. Let's see, N is moles and V is volume, like liters. So that actually is moles per liter. So guess what? That actually is molarity. Okay? So now what you're going to see in the proof is instead of molarity, since they're all gases, I'm actually going to plug in the partial pressures, okay, for each, for instance, for the molarity of A, I'm going to break it out. I'm going to say the partial pressure of A divided by R and T. Okay? I'm going to do that for everything. That's A. I'm going to do it for B, C, and D. Okay? So it looks a little weird, okay, but again, this is a proof to basically say then that equilibrium constant in terms of molar concentrations is equal to this in terms of partial pressures. But see, here's the deal. We might want to say, wow, that's pretty easy. We got our R's and our T's. They all cancel out. Not so fast. Not so fast. They are all in common. R's and T's are all in common for everything, but they're raised to a stoichiometric. They're raised to the stoichiometric coefficient. They have a power associated with them. So we can take this and distribute the exponent through that quantity, okay, and it looks like this. All I did was just distribute the exponent through the quantity, pulling out our 1 over RT's, and it looks like this. Again, kind of regrouping, our 1 over RT's can actually go into one common 1 over RT, but we have to pay attention how we're going to handle this in one term. And then I'm going to gather the partial pressures together. Okay, so here's the partial pressures all gathered together. Again, the partial pressure of each component raised to the coefficient that's in front of it in the chemical equilibrium. Over here we have the 1 over RT, and in order to mathematically make it right, if the exponent is in the numerator, it's actually added, okay? And then from that, we subtract the sum of the exponents that are in the denominator. Okay, so that little 1 over RT raised to that power, this is that power. If you go back, you can see it. Okay, this is that power. where basically those are stoichiometric coefficients of the products minus the sum of the reactants. And that is referred to as delta N. Delta means change in, so that's change in moles. That basically is the change in moles. So here we go, and I think that this might be in a box coming up, I'm not sure. Maybe or maybe not. But actually, if we go ahead, instead of having that, quantity C plus D minus quantity A plus B, go ahead and put delta N there. That's the change in moles. So basically, you're going to look at the products, add up their coefficients, and you're going to subtract the sum of the coefficients on the reactant side. That's your delta N. Okay, kind of cleaning it up, getting it to something that feels a little bit better. There's a blue box again, so that actually we've kind of arrived at something that might be helpful. So again, it's the same chemical equilibrium, okay, and everything has to be in a gas phase. But the Kp value for that equilibrium is equal to the Kc value times the ideal gas law constant times the temperature, and I think I have a note here, temperature needs to be in units of Kelvin raised to whatever the change in moles are for the equilibrium. Oops, sorry. Yeah. Where the value for R that we're going to use is that liters atmospheres per mole Kelvin. Okay. And the partial pressures need to be in units of atmospheres if we use that value for R. So let's look at a real live example. Oh, I printed these off and I forgot to bring them. Oh, well, you're going to have to kind of, because I don't have that one memorized, but using that blue box for the relationship between Kp and Kc, if we're given Kp like this, we could get to Kc. So we're going to need to know what our delta N is, our change in moles, and it's the sum of the moles on the product side, which is 2. From that, we subtract the sum of the moles on the reactant side, which is 1. So 2 minus 1, delta N is 1. Delta N could be negative, actually, if you end up with fewer moles on the product side than you do on the reactant side. Okay? We're going to have to, in that relationship for that blue box, we're going to have to use, I'm trying to think if I give you that on the exam, I can't remember. But we're going to have to use temperature in units of Kelvin, not Celsius, so we got to fix that. Okay, so this is what was in the blue box. We're going to rearrange it because we know Kp and we're solving for Kc. Okay, so not too bad. So now we're ready to plug in our Kp, the ideal gas law constant, and our temperature, and the delta N is 1, right? So this is what the Kc for that same equilibrium is, given the Kp. So the Kp value was 0.62. Remember, Kp's and Kc's are unitless, those equilibrium constants in terms of molar concentrations or partial pressures. So 0.62 divided by 0.082058 atmospheres liters per mole Kelvin times the temperature in the Kelvin scale is 318, all raised to the first power. Round it to 2 significant figures. Okay, your Kc for that same equilibrium is 0.024. And that's it. So here's some assignments that go along with that. And we'll kind of take a quick look at 4, 6, and 8. And they look like this. So 4 looks like this, where you're given, let's see, is that all I say? Oh, yeah. See, these aren't too bad. I say that about all these, right? So for these, all you're supposed to do is say Kp is equal to, and then for instance, the first one would be the partial pressure of CH4 raised to the first power times the partial pressure of H2S raised to the second power divided by the partial pressure of CS2 raised to the first power times the partial pressure of H2 raised to the fourth power. See how that goes? Yeah, so you don't have to, oops. Come back here. Only does what you
Hey,
want.
Ms. Snipes, may I ask a question?
Yes, ma'am. Yes, sir.
How do you denote the partial pressure of a molecule or atom?
That's a good question. I probably would, I think to be fair, I think you have to write the whole thing. So it's going to be, for instance, in your numerator, it's going to be the partial pressure of CH4, like
Oh,
that.
that.
Like little
Okay.
subscripts, yep. Partial pressure of H2S squared.
Okay.
Yep. Times partial pressure of C. These are fun. CS2 raised to the first. Oh, raised to the first power. And then, last but not least, the partial pressure of H2 raised to the fourth power. I should say is equal to Kp. My bad. So, just to kind of get you used to writing them. Okay, so the next one looks like this, where I just did the first one for you. It's one of those where you get to write the equilibrium. So it says for the formation of 1 mole of NaCl. And so I went ahead and put down the product side because it's formation, chemical equilibria. What's it going to be made of? Well, it's going to be made of nitrogen, oxygen, and chlorine. That's cool, but they're all diatomic elements. So it's going to be N2, O2, and Cl2, which to balance it, you're going to put what? 1/2 in front of each one of those, aren't you? And then you're going to go ahead and do it like you did on the previous problem. For this one, this is like we just did a minute ago. Instead of, though, given the KPs and asked to find the KCs, we're given the KCs and asked to find the KPs. So determine the KP given these KCs. So you don't have to write the equilibrium constant expressions. All right? Okay. We'll see. Coming close. We go till the top of the hour, don't we? Just kidding. Okay. So, equilibrium constant expressions. There are times when you'll want to reverse your equilibrium, like it's written from left to right. You want to go ahead and swing it around your equilibrium arrow. There are times when you want to basically divide your whole equation by 1/2. You know, multiply the stoichiometric coefficients by 1/2, or multiply the stoichiometric coefficients by 2 or by 3 or something like that. There are reasons for wanting to do that. And if you do that, you end up with a new KC. And actually, we're going to talk about what that new KC will be. So we're going to call this equation 1. So if you want to put a 1 there, you can. So notice, and you guys had some practice at this, the solid's not going to appear, right, in our equilibrium constant expression. So our equilibrium constant expression just looks like this. The molar concentration of SO2 raised to the first power divided by the molar concentration of O2 raised to the 3/2 power. That's it. That little subscript 1 there comes from the fact that we're going to call that equation 1. Well, we could take the same chemical equilibrium, multiply it through by 2, and check this out. It looks like this. Well, now we have 2 moles of S react with 3 moles of O2 to form 2 moles of SO3. All I did was multiply through by a factor of 2. We can call that equilibrium constant C2, and it's going to look different, right? It's going to be the molar concentration of SO3 squared divided by the molar concentration of O2 raised to the 3rd power. What these have in common is the same chemical equilibrium. They are related by basically quantity raised to the 2nd power. Let's see if I got that. And you're going to have to convince yourself. If you go back and compare KC1 to KC2, to get KC2, you actually had to take KC1 raised to the second power because you multiply your equilibrium through by a factor of 2. So whatever your multiplying factor is, that's what you raise your KC to that power. Okay? So that's trick number 1. Trick number 2, and if you want to call this equation 3, you can. Wait, no, this is equation 2, isn't it? Yeah, don't call this equation 3. This is equation 2 again. You probably recognize it. What if we swing it around the reaction arrow? It would look like this. So instead of SO3, 2 SO3s being over there, 2 SO3s here, okay, you know, our reactants now are products, we have 2S plus the 3O2. Again, to write our equilibrium constant expression, the sulfur does not appear because it is a solid. So our equilibrium constant looks like this. And you could call this 3 if you want to. This is equation 3. Equation 2 from before, and this is equation 3. So notice then we have O2 raised to the third power, it's the product, divided by SO3 raised to the second power. Okay, so that's our equilibrium constant expression. And you might see what these have in common. One is the flip of the other. So it's the inverse. So we could write that mathematically like this. So if you ever, like for instance, you knew K2, okay, but you wanted to know K3 and you reversed it, basically you take 1 divided by K2, and that will be your equilibrium constant for the reversed equation. So that's our other trick. All right. Oh yeah, there's 3 tricks. This is the third trick. I was like, there's one more trick. So we've talked about elementary steps. I'm not saying these are elementary steps, but we kind of talked about how you can add 2 things together to get an equation of interest. Let's just say we are going to add those 2, and notice our COs are going to cancel, our CO2s are going to cancel, right? You know. So the net equation, or the equation of interest we get by adding equations 1 and 2 is now equation 3. Okay, so like I said, our COs have canceled, our CO2s have canceled. We bring down our iron, we bring down 1H2O, we bring down the FeO, and we bring down the H2. Okay, 1 mole of everything. Well, and in fact, I think I left room so we could do this. Let's just, you can do it on yours, and I'm going to do it on mine. Underneath equation 1, I'm going to go ahead and write up here what the Kc expression is. I'll call that Kc1 is equal to the product, CO, this one doesn't appear, right? Raised to the first power, divided by the reactants. This one doesn't appear either. Molar concentration of CO2, also raised to the first power. For our second chemical equilibrium, okay, the products, both of them appear. H2 raised to the first power, CO2 also raised to the first power. Looks like both of the reactants appear. H2O raised to the first power. I said H2O does not appear if it's an aqueous solution. I don't think this is an aqueous solution, so it does have to appear. Molar concentration of CO also raised to the first power. Down here for our equation of interest, we're going to call that equilibrium constant, Kc3. Remember our iron doesn't appear. Molar concentration of H2 raised to the first power divided by molar concentration of H2O, also raised to the first power. So I am on the next slide going to show you how actually the relationship between these 2 will give you this one. So it looks like this. Okay, for the first equilibrium, this is what the equilibrium constant expression is. The second equilibrium, now it's got an intermediate in it. Watch out. It looks like this. If we were to, here's the trick. If we were just to basically pretend this isn't here and go ahead and multiply these 2 together, look what happens. Those cancel, these cancel, and that's what I'm left with. If I just multiply them together. And that's the deal. That is the deal. If you add 2 equations together, equilibria together, like we did, I guess they'd have to be chemical equilibria. If you add them together and you know their KCs, okay, you actually know the KC of the sum, the overall reaction, is actually just going to be, you have to multiply the KCs together, just like we did. That's the third final trick. So let's look at one in action. So on the next slide, you already have, on the next slide, you can look at 3 different ways to look at this chemical equilibrium, where NH2 plus, N2 plus H2 go to form NH3. There are 3 ways to balance that equation. Okay, we're going to say that we go ahead and let this settle, and at equilibrium, these are one set of equilibrium concentrations at this particular temperature. Okay, so a few slides ago in this part, clear back, these would be the gray concentrations, the ones that have leveled out. All right. So this is one way to look at the balanced chemical equilibrium. 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3. Okay, now we could go ahead and write the equilibrium constant expression for that. I'll put all of these up. There they are. Okay. These are all talking about the same chemical equilibrium. And actually we're going to refer to these as equations 1, equation 2, and equation 3. Okay, for instance, you see the difference between 1 and 2 was we switched it, right? And the equation between 2 and 3 was that we took it times 1/2. Okay, so let's take a look at their equilibrium constants. Now, one of the things you haven't had much exposure to yet is basically calculating KCs. And if you're like me at this point, like, how would I come up with a KC? Well, all you got to do basically is, these are equilibrium concentrations. We're basically just going to substitute these molar concentrations in for those where they should appear. So let's do it. Okay, the KC, I should give you enough time. I think we're probably okay with how we came up with the initial expression. The equilibrium constant expression. Look at the products, which is only 1, raised to the stoichiometric coefficient, divided by the reactants, raised to each of their stoichiometric coefficients. This is a really good way to do this problem, where basically it hits you over the head. Notice the little E means equilibrium concentrations. So we had the ammonia equilibrium concentration of 0.016 molar, the nitrogen equilibrium concentration of 0.030 moles per liter, and the hydrogen concentration, equilibrium concentration, 0.037 molar. So we're just going to plug those into our equilibrium constant expression. Go ahead and do what we need to do mathematically and round to 2 sig figs. And we have a KC of 1.7 times 10 to the second. And we pack it up in scientific notation so it's easier to see that we have 2 sig figs. But are we all on board that this is really 170? So KC1 is 170. Remember, those are all unitless. So what we said we did between 1 and 2, if you look back the previous slide, we said we reversed it, right? So let's check this out. Okay, this is the K2. This is the second equation. So what would the KC look like? KC would be N2 raised to the first power times H2 raised to the third power, okay, divided by NH3 raised to the second power. So that's our equilibrium constant expression. We have the same equilibrium concentrations. We're going to plug in the right place. So plugging in our equilibrium concentrations, we get 0.030 raised to the first power times 0.037 raised to the third power. In the denominator, we have 0.016 raised to the second power. I'm going to tell you, working these problems, it's really easy for your eyes to go buggy and for you to get the wrong equilibrium concentration in. I've done that. But just take your time. So you round to 2 sig figs, we get 0.0059. And as you see in the blue box next to that, 0.0059. If you were to take 1 divided by 0.001, 0.0059, you would get 170. Okay, if you were to take 1 divided by 170, you would get 0.0059. That actually is the reciprocal of 170. Because equation 2 is related to equation 1 by reversing it. So it's just kind of a little mini proof there. So one more equation, equation 3. And equation 3, if you look back a few slides ago, is related to this equation by multiplying through by 1/2. So here we go, equation 3. If you were to write the equilibrium constant expression for this one, it would be N2 raised to the 1/2 power times H2 raised to the 3/2 power divided by NH3 raised to the 1st power. So you're ready to go ahead and plug in. So Kc would be equal to 0.030 raised to the 1/2 times 0.037 raised to the 3/2, all divided by 0.016. Rounding it to 2 significant figures, you get Kc3 is 0.077. And indeed, if you take that second Kc, 0.0059, and raise it to the 1/2 power, which is what you got to do to get your third equation, you do get 0.077. Okay, so that's kind of showing it in action. So these will also be due, but I will post these. Let's take a look at these. Part C. So here's your first one. I kind of teased, this totally reminds me of Hess's law, but it's not really, but it reminds me of it. So the star is your reaction of interest, and 1 and 2 are your puzzle pieces, basically. And what I did was to go ahead and notice, I said, for instance, where it's purple, I said I would focus on the N2 there to know how to use equation 1. Okay, the fact that you want 1/2 mole and it's on the reactant side, guess what? You're going to have to take it times 1/2, because you only want 1/2, and you're going to have to swing it around. I usually say swing it around, I usually show as a negative. Okay? But when you do those two things, your Kc, you're going to have to what? Take it to the 1/2 power and take the 1 over it, the inverse of it. And I went ahead, and if you have to go, that's fine. So it won't hurt my feelings, but I'm just going to go ahead and finish. So the green, actually I gave you the hint here that I would focus on the 1 mole of NOBR. Check it out. You got to buy on that one. You need 1 mole on the product side. Okay. So that shows you how you need to manipulate them. But then the catch is, okay, remember when you're reversing, blah, blah, blah. Okay. Yep. We got that. At the top of this slide, I went ahead and told you, finally, when you're adding them, okay, that could be your reaction of interest, be Kc3. Remember that you're actually going to be multiplying your new Kcs. Okay, kind of like we talked about. So let me know if you have any issues, because these are all very similar. Okay, again, the reaction of interest got the star next to it. You have 3 reactions to get there. Okay, and I gave some hints for the first 2. For the third one, is this the one I'm thinking of? For the third one, it's down here in green. You have some choices. Basically, you adjust your third one so that it cancels out your intermediates N2 and NO2, okay? Or you focus on O2 that you need in your overall reaction of interest. But remember that O2 is also created in equation 1. So here I said, use process described previously to get Kc, the reaction of interest up there, your 3 reactions, your equilibrium. And then you're going to use the relationship between Kc and Kp to get Kp. And here's a similar one. The reaction of interest, 3 equilibria. So you're going to get Kp and then get to Kc from there. And last but not least, this is a good one. So basically it says that there's your chemical equilibrium of interest. It gives you temperature of interest, which you're not going to use really. But it says at equilibrium, these are the grams of the product, which is the PCl5, and the 2 reactants. That's the mass that you'll have. It gives the volume, okay? And are you guys remember how we can get from, we can take the grams, convert it to moles, divide the moles by the volume to get our molarity. That's basically the trick here. So to get your equilibrium concentrations, you're going to have to do that. Your equilibrium constant expression looks like this. Okay, so I said you're going to take those grams and consider the volume to get to the molar concentrations and plug up there. So that actually is kind of like what we did with the ammonia. You're going to get equilibrium concentrations, molar concentrations from these gram concentrations. Plug them into your Kc expression and get your Kc. And then to get Kp, you kind of use the relationship with the delta N, okay, from your Kc. All right, das is das. And we'll pick up here